All right. Well, welcome everyone. My name is Roxy and I'm the chair of the Sustainability Committee for AIC. And I'm here with Rachel, who's our vice chair, and Belly, who's our student member. And we're speaking today with Mark Nussbaum, who is a principal engineer at Architectural Consulting Engineers. And Mark has expertise in sustainable systems, specifically for historic buildings, which is really awesome for us. And he is also a project manager and consultant on the NEH project with the Glessner House, where they are installing geothermal systems in that historic building in Chicago. We did part one of that series with Bill Tyre, who is also working on the project. And so now we're going to speak with Mark, who has a little bit more technical, or a lot more technical expertise in the area of specifically geothermal. So to get us started, Mark, can you just give us a little bit of background about your training and what made you interested specifically in sustainable systems for historic buildings?
Sure.
Seems like, yeah, go ahead.
Yeah, it's kind of an unusual place to find yourself. First up, most engineering firms don't really like to climb into historic properties because it's hard work, it's time consuming, it requires a lot of expertise. And usually the budgets just aren't there. Usually it's a lot of times with not-for-profit organizations. And so they just can't afford high consultant fees. So since I work for myself and I've started my firm with the intention of working in this field, I get to pick and choose the projects I work on. And when I've been very fortunate to work on some really cool projects over the years. I had a background in my first job in this field. I was an engineer for the city and county of San Francisco, and I did a report for, this is back before the Loma Prieta earthquake, but I did a report on the upgrades required for the historic Civic Center district, which was 7 historic buildings built after the earthquake in 1906. And so that, that kind of pushed me in really quickly into historic properties and the working on them and finding out how cool that is. And so then, throughout the years, I've had opportunities when I work for other firms to do other historic based projects and kind of developed that philosophy of trying to integrate modern systems in historic buildings without tearing the building apart as a driving concern. and that was a strongly resonant feeling with the architects that I contacted and ultimately have worked with many of, because I think a lot of engineers are reluctant to do something that's not going to produce the best optimal engineering results. And so I try to take the attitude, I'll give you the best engineering solution I can with as minimal damage to the building as possible. And so by taking that approach, and I offer both approaches to the client. I'll say, well, I can tear the heck out of your building and get the system just perfect and they'll work great and will be very invasive. And if that's what you're looking for is a perfectly operating system, performing system, I can do that. Or I can do it this other way that does as little damage as possible and get you a perfectly adequate system, but maybe doesn't achieve everything. So, and they always take that second choice. And then I remind them of that if we have a situation where the system doesn't do exactly what we had hoped it would, or if it's just not as optimal. Because you can deliver air into a room from across the room, where you have access to put a duct without compromising, or I can tear up the ceiling and get that air device out there by the outside wall, which will probably perform better. So we just, that's our focus. It's just to try to introduce systems, and that revolves around spending a lot of time on the site, crawling every interstitial space that's available to me. I've been in more attics and crawl spaces and tunnels and really cool spaces in these buildings. And have found rooms that they didn't know existed in eaves, large spaces in eaves where I've been able to put equipment and effectively hide it from and not even take any of their precious space because I was able to hide it someplace they didn't even know they had. So
really interesting. Wow.
And then over the years, I've worked on getting. I started doing geothermal systems or ground source heat pump systems before I opened my own firm when I was down in the St. Louis market. And when I moved up here, it wasn't really viable here because of the utility rates were structured and efficiencies weren't as high as they are today. And but I was asked to put a proposal on at Unity Temple. Frankly Wright designed building in Oak Park here, and they specifically wanted to look at geothermal. So and so I ended up getting that commission, and in 2004, and then 11 years later, after the study and a bunch of other work we've done there, we actually started the restoration process and completed that in 2017. So and using geothermal. So but that reintroduced me to geothermal or ground source heat pumps up in this market, and so I started looking at that from various projects to see how it could be implemented. And again, the technologies have changed a little bit. The drilling techniques have changed a little bit to make it more possible on these tight urban sites that we have up here.
That actually transitions brilliantly to my next question.
Let's see, it's almost like I knew.
That's so interesting. I love the kind of like problem solving. Obviously, we're in the conservation and preservation field, so we love to hear people who are willing to take on these projects and figure out how to do it without hurting the building. So that kind of, like I said, leads me on to my second question. So we're really, I mean, we spoke with Bill, but none of us were engineers, so we kind of didn't get too close to the technical aspects. But I wondered if you could give us just a sort of brief layperson's understanding of how geothermal works and why it is then appropriate to use for historic buildings.
Okay. Well, geothermal systems or ground source, I mean, it's kind of an interchangeable terminology. Sometimes geothermal gets confused with the deep earth heat type of geothermal, where we're tapping into a hot source down underground due to the proximity to magma, and we can either use steam generated from that or other things. This is not that. So what I'm doing is I'm drilling into the ground anywhere from, in this area we drill anywhere from 150 feet down to 500 feet vertically down into the ground, and then we separate those pipes roughly 15 to 20 feet apart, and then we can then we put in as many pipes as we need. And we circulate a fluid through that glycol water mixture, so it's antifreeze, and we circulate that, and then we circulate from that field into a box, and that box is usually inside, and it has a compressor, and then depending on how it's being used, it may have a fan and be like a furnace, only with the air conditioning part that sits outside in a traditional air conditioning system. It sits inside this box, and then there's a heat exchanger for the water loop. And so we leverage the work of the refrigerant. So think of a refrigerator that sits in a room that's 70 degrees, and somehow I produce 0 degree freezer and 40 degree or 35 degree refrigerator temperatures, but it's sitting in a room at 70 degrees, and it's using the work of the refrigerant to do that. If I think of an air conditioning system, when it's in cooling mode, which is what air conditioning does, inside it's blowing cold air out of the furnace box. I have a coil in there, and then if I go outside to the outside box, it's blowing hot air. And because it's exchanging energy from inside the house, it's moving it to the outside. And it can do that up to temperatures of 95 or 100 degrees with still keeping full capacity in the box. With a heat pump, there's a reversing valve in that refrigerant loop, which then switches the function of those two coils. And so in the heating mode, it blows cold air outside and blows hot air inside. With a geo system, instead of interacting with the air of an air source heat pump, or an air source cooling unit, I'm interacting with the ground loop, and that deeper temperature varies across the country depending on how far north you are. In the Chicago area, if I take an average temperature of that 500-foot loop in the ground, it's about 52 degrees. And so so we start to put heat in the ground during air conditioning mode, moving it from outside the building into the ground, and slowly start to elevate that temperature in the ground loop. And then when we go into heating mode, I start to extract that heat back out of the ground because it acts kind of like a storage battery. And then over the course of the winter, I bring the temperature down below that average temperature. The average temperature stays about the same. It just cycles like a sine curve. It just cycles across the seasons. And because we can control that temperature swing by how much pipe we put in the ground, we can keep it at the optimum equipment efficiency range. And so the geothermal heat pump system is the most efficient system, so it's got the lowest operating cost of any system on the market. So what makes that, it does cost more because the ground loop that you got to put in the ground, it costs a whole lot more than that box that sits outside in a conventional system. But it allows me to have full capacity year round out of the box, which I don't get in an air source heat pump. I don't have any exterior equipment that pollutes a site with aesthetic or noise. And then if I configure it correctly on the inside, a really important point of the system is that I can get simultaneous control of temperature and humidity, which is ideal for historic projects where we're trying to dampen that swing. In historic properties, usually the buildings aren't designed for air conditioning and controlling humidity, so we have to do that very carefully. But I can usually chop off the extremes, the highs and low humidities. I get very stable temperature control, and then I can achieve a really good, acceptable relative humidity control, or at least improve it dramatically. Which, of course, comes to what you guys like, which is that nice, stable, within plus or minus.
The heart emojis. I'm like, yes, please.
Yeah. So that's. I once sat on I was on a project for the National Trust at a project out in Washington, D.C., where they set all the conservators around the table, all the different types of conservators, so building conservators, the paint and paper and paintings and all these different, cloth, and they sat around the table and told me all the things that they like to restrict and how they like to have control of the environment. And then they turned to me at the end of it and said, "Okay, fix it. Give us a solution." So
you've been through the worst of it then. We're nothing.
Because of course we can't get everything perfect. The buildings are the limitation of what we can do. So if the building can sustain higher winter humidity, then we could add humidity, improve it. Usually the summer is easier than the winter because it's easier to shave off humidity in a building in the summer than it is to add humidity in the winter. I mean, it's easy to do, but you run the risk of introducing a problem in the building, much more risky in the wintertime than it is in the summer.
Interesting. Well, again, this is a good transition. Unfortunately, Rachel said her internet was going in and out, so I'm going to ask her question.
Okay.
But hopefully she'll be back and can hear some more of your interesting feedback. So we were kind of interested in how you make that transition. I mean, that seems like certainly the stable humidity is a huge benefit from our point of view, as you well know.
Right.
But when you're working with an older home, and I guess it probably depends on when the building was built, but is there kind of a typical infrastructure that you would be converting from, or particular infrastructures that work better to convert to geothermal? If a museum has gas, forced air, or say, or I don't know,
Sure.
I mean, you know more than me obviously about what the options are, but can you talk us through that process a little bit?
Sure. Yeah, if the building currently has forced air, that's perfect. You do have to be a little careful. If it's a heating only system and I want to introduce cooling, I have to be concerned about the ductwork having insulation. And so a lot of times residential properties don't have any insulation. So that's something you have to address. You either have to take the sheet metal off and get it insulated or replace it, because if I put really cold air in there and the building is humid, it'll condense the outside and drip onto the objects of the building envelope, which then can cause mold growth and all that stuff. But it's still usually, that means there's space already encumbered with ductwork, and so I can usually get it in. And then the equipment's just a direct replacement at the equipment. Remove the furnace and put in a heat pump. So it's pretty straightforward. I can also make chilled water and hot water from a heat pump. So chilled water, so a lot of systems, especially commercial systems, operate with a fan box with a water coil in it that blows air across the coil, and you run chill water through the coil, or you can run hot water through the coil. And in our case, we have two coils. We have a chill water coil and a hot water coil in sequence. So again, I can make mechanical cooling generally removes humidity from the building. So it just has a course of the, so the air temperature gets brought down below the dew point of the air, which causes the moisture to come out. But the problem with that is if there's a high humidity level and not a lot of cooling load, in other words, it's maybe spring or fall, or it's designed for a large occupancy and I don't have anybody there, I can reach my cooling set point before I reach my relative humidity set point. So then having the coil set up as cooling first and heating second, I can run the cooling side to get down to temperature. When I satisfy my temperature set point, I continue to cool, but then I reheat the air coming off the cooling coil back up to room neutral temperature. So I don't continue to cool the space. So I can control that temperature and then I can bring the humidity down. So in either one of those systems, I can do that with the refrigerant side on the heat pump. If I have a forced air heat pump, I can do the same thing. I use the warm water in the loop after it's gone through to circle back around and reheat the air when it's called dehumidification mode. If a lot of historic buildings don't have a forced air system, they have radiators, a cast iron radiator that's running on steam, which is common, is not directly exchangeable with a geo system. About 120 degree water. So that's really in a steam boiler. A steam boiler is going to give you about 220 degree steam. It's about 5 pounds pressure, and 212 is boiling point, so it's a little higher than that. So the building is designed around steam heat. I actually may or may not be able to get enough heat out of that radiator with lower temperature water. So you have to look at that. Oftentimes you can, because we improve the envelope, we add insulation. When the building was built 100 years ago, it probably didn't have any insulation or minimal insulation. They had leaky windows, air infiltration wise. So we have a lot of extra loads. And they usually over-design the radiators because 100 years ago, they were going through the Spanish flu. And the health design of the day was to introduce lots of fresh air into buildings. And so they oversized the radiators. And so you could bring in fresh air and it would rise out and be ventilated out the upper. So they were dealing with the same exact issue today, 100 plus years ago. And that's real common. You get these mansions, they'll have floor radiators, box radiators to sit at the basement level and open up to a cast iron grill on the floor. And then there's an outside air duct that goes off that box radiator in the basement over to a window opening or a louver in the wall. And they bring in fresh air that way. And then they open the windows. So anyway, so you can sometimes get by with a lower temperature, but usually you can't, with just heat pump water, with no extra boost to it or anything, I can't get enough heat out of that. So I have to rely on a second stage of forced air, because if they want cooling, I'm gonna have to do forced air. So that's, so I'm gonna introduce a forced air system on top of a radiation system. We usually like to keep the radiators in place because they help drive moisture. They sit usually below the windows, and the window is the leakiest spot from water infiltration, just by the nature of a big opening in the side of a wall. And so we usually that's where the radiator's at, and we like to keep that drying. So it doesn't matter if an envelope gets wet; it's fine. It should be designed to get wet, but it also should be designed to dry out. Because if it doesn't dry out, it rots. You get mold and rotting wood. So we like to keep the radiators in place. I do in my designs, and so sometimes we'll still keep natural gas boilers to produce hotter water if we feel like we need hotter water. But I'm working on a project right now. It's a Frank Lloyd Wright house, and the owner would like to take it to a net zero, which means I produce as much electricity on site as I use on site. And so that doesn't work with natural gas because I don't produce any natural gas on site. And so we have to get rid of all the natural gas sources, and she's got cast iron radiators. And so I'm using a 2-tier heat pump. They make a heat pump. The normal heat pump gives me about 120 degree water. And then I can put in a special heat pump with a different refrigerant that'll give me up to 160 degree water, 160. And so I can produce I could produce hot enough water to make those radiators work without using gas heat. So
that is really neat. Gosh.
did I answer your question?
Yes,
Again,
you did, for sure.
I told you I get kind of off topic sometimes.
No, no, no. Well, I'm fascinated by all of this, so that's all good. So it sounds like there are particular systems. It sounds like the forced air system is really the easiest, and then you have to kind of just. I imagine it's sort of a case by case basis how you
Very much
it.
so, yeah. I mean,
Yeah.
in a residential application, not historic, we usually, I mean, like I said, if you want cooling, I'm going to have to insert ductwork. And so a lot of times in a residential application, they don't, even though they might like radiators, they're willing to get rid of the radiators, or, it's not a big deal. Yeah, it's a forced air system, either if it's already existing, or if they want cooling, we're going to add a forced air system. That's the least expensive and simplest to control. And because I also, if I want to introduce humidity in the space, usually I'm going to do that through the forced air system, and then removing humidity through the forced air system. And while there's other ways to do it, that's the simplest way to do it. And so,
yeah, I think that's really good for people to know if they're thinking, at my institution, is this something that would be feasible, or my historic building or whatnot. Is the process, I mean, you've kind of already answered this, but how extensive and sort of invasive is the process? Again, like you said, it's a case by case basis, but it sounds like you're able to kind of use some tricks to make it not too invasive. But are there kind of interesting examples of ways in which you can do that you could share?
Sure. So let's just think about a typical 2-story house with an attic and a basement. That's about as easy as it gets for an installation, because I can service the first floor in the basement from the basement. Usually it's utility space, and so it's okay to have exposed ductwork, or you usually have more utilitarian uses, so we'll call it secondary or tertiary spaces in the historic places, off tour, if you will. The attic gives me the same thing, with a caveat. I want to see them insulate the roof deck. That's at the sloped roof, or it's a flat roof. I want to see the insulation up in the roof rafters, so that my attic space is a semi-conditioned space, because the equipment we're going to put up there is going to perform better, have a longer life, and have less problems if it's in a semi-tempered space. It doesn't need to be room temperature, but it shouldn't be 0 degrees in the wintertime and 120 degrees in the summertime. It should be, so you insulate up at that roof line, and then you take the insulation out. If there's insulation in the ceiling, which there often is, even in older buildings, you take that out so that heat can get up there. The heat and cooling can get up there. So that's really straightforward. Then I'm serving usually floor grills from the basement level, and then ceiling grills from the upper level. And you have to think through the process of getting to the house on tour. Usually, we had that conversation with the client to say, we can, if there's examples of forced air grills in the house, and it's got a particular pattern, a lot of cast iron grills are very elaborate and stuff like that, we can recreate that in a custom grill. And so we keep that same basic pattern, so it looks like it was maybe always there. If there was never forced air in the building, or there aren't any examples of grills in the house that we can buy off on, then we have to make the decision: do we try to hide the grills so they're less obvious, or we just put in modern grills and then interpret it as part of it? Well, this is our modern system, and you don't try to hide it. So that's a kind of a client decision, and kind of again, there might be easy ways to hide it, and there might be hard ways to hide it. So we kind of talk through that with the client. When you get into a 3-story house, where I've got a basement below, first, second, third floor, and then an attic, the second floor becomes a problem, because I don't have utility space above or below it. I've got finished space above or below it. So now you have to start looking for opportunities to hide equipment on that floor. So a lot of old houses have decent closets, and so I can maybe put a small unit. It's easier to get piping through the building without tearing the building up than ductwork. And so I'll put a fan box in there, and this is where it will often make a decision to go to a chilled hot water system versus a direct geo system, still served by geothermal equipment, but you add the complexity of the pipes and the pumps, because I've got spaces I don't want equipment in. I don't want geothermal equipment in, because there's a compressor in there, and while it's fairly quiet, it's not as quiet as just a fan box. And so, so you'll put a fan box, a fan coil unit is what we call it, up in the usually at the ceiling of the closet. And then we'll create a grill, maybe on the sidewall, just above the door jamb, just above the trim. So it's linear like the trim, and maybe, you know, disappears a little bit. And then we go into the room and return into that space. So you start looking for those opportunities or other utility spaces on that floor. Sometimes, you know, you might have a setup where they're willing to drop the ceiling in the hallway, for instance. You know, it's maybe a 10-foot hallway ceiling, or maybe even more. Sometimes, you know, they'll have very generous hallways. And so you can put equipment in, put ductwork at the ceiling, drop a new ceiling below, keeping, you know, moving the code molding or whatever that's elaborate. And then you go sidewall off, you go to side grills in the rooms off of that type of a system. So those are another method to use a fully ducted system if you've got a place to bring the duct up and hide the equipment. So, but yeah, those types of spaces with that third floor finished, generally create a much more challenging trying to figure out. But and
it sounds like the biggest. Oh, sorry.
I was going to say that I actually had projects where they didn't want to do that, so we conditioned the third floor and we conditioned the first floor and let the second floor kind of, it's semi-conditioned. It is conditioned there that finds its way. It's just not as effective. So anyway, so you follow up.
Yeah. So the limitation is really that sort of hiding space, for lack of a better word.
Yes.
That's kind of the biggest. Okay, that's really good to know. I had no idea.
Well, we've done projects where we've, you know, if they have radiators and we can put a fan coil unit, a vertical fan coil unit that hides in, you have a radiator, maybe with a radiator, a wooden grill in front of it or a casing around it. We can actually put a piece of equipment to replace that, a heating cooling unit, a self-contained unit right there. It does introduce more noise in the space because I've got a fan powered unit inside the room, just hidden by a wooden screen or something like that. So it tends to bring in a little more noise, but we do that as well. We've done that as well. So.
Belly, I'll toss it over to you to ask a couple questions because I think we've got through most of mine.
Okay.
Sure. So you've touched a little bit on a couple different projects that you've worked on, all of which sound fascinating. I was wondering if you could speak specifically to your work with the Glessner House.
Sure. I've been involved with Glessner House for a long time, well before 2 or 3 executive directors before Bill. So Bill Tyre. So I've done various projects there, but we had done he was intrigued by the geothermal concept, and they had us look at it, do a feasibility study, and it came out that, you know, it was a little more cost than what they could afford at the time. And then he got a donation, and we were able to, this back in 2015, I think, 2014, 2015, where got a donation to do a partial system. So we designed the whole building, and they had replaced, and I want to say it was done in the 70s or 80s. They replaced the original system that was there. And I'm honestly not, I think it was just a radiation-based system. I'm not 100% sure of that because there wasn't a lot of evidence and there were no drawings. But there was a forced air system that was in place there, and it was most areas were just heated, no cooling. A couple rooms had cooling in them because it wasn't a house museum. I think when they did the project, it was just offices, an event space. So anyway, we looked at areas that we could reuse the duct runs, the ducted equipment, and then areas where we couldn't, and then we designed a system, and it consisted of, I want to say they had 9 or 10 systems, or maybe even 11 systems now throughout the building, and we replaced that with a design with 10 systems for replacing. And the equipment's located where the other equipment was generally, so we're just taking a box out and putting the box in, but in most cases we're providing new ductwork because, again, it's not insulated, but we are trying to reuse all the existing floor and ceiling openings that we can, because, you know, that way we're not making new openings through historic building. And then there was 2 spaces that the coach house, or the garage, if you will, that space sits at one end of the building, and that had a air conditioning system because they used it for events, and And then the second floor above that was an unfinished space that they were hoping to finish into a gallery type space. And so we designed for all the areas in the building, sized up a loop field that was based on 4 500-foot deep Rygan pipes, which is a traditional geosystem uses just a pipe that goes to the bottom of the hole and comes back up. This is a specialty system that when you have limited space, you pay more for the product, but you get more capacity out of the loop field. So it was worth it, since the side yard there, the courtyard is very limited in space. And so we needed to get the well field in. So we designed the system and we bid it out, and they could afford one. We afford half the well field, two holes, and then one system inside. And so we replaced that in like 2015, and that's been operating. Then Bill applied for the grant, and when he got it, then we're massaging the plans to update them for current technologies and model numbers of equipment, and we're going to remove the heat pump from the unfinished space above the carriage house, because we're pretty confident we won't have the budget for that. And then we're going to add the additional well field, and then slowly sequence in replacing the systems over the course of the grant timetable. And it's getting tricky, because we're trying to get the drilling done. We were trying to get the drilling done this fall, so he could get his grass sodded, his sod installed before the winter. I'm sure he mentioned that. But we've run into an obstacle with the city of Chicago, where they require what's called a board of underground review, which if you go deeper than 10 feet below ground, you have to go through this review process with all these agencies and around the city to make sure that we're not getting into any of the underground infrastructure that supports the city, like the subways and things like that. Now, ironically, when we drilled the well field 4 years ago or 5 years ago, we didn't have to go through that review. So I don't know if something changed or whatever, but we're going through it right now, and so we still think we can get the drilling in. The driller said he can drill down to about when it's 25 degrees Fahrenheit. Below that, it gets to be a problem, because we're circulating water and it's really cold for his crew. So we hopefully will get be able to drill over the winter, so that we can start installing systems after the heating season. So.
Yeah, that would be great. I was fascinated when we spoke to Bill, or I guess just really impressed by how you all have been able to make this work within such a small system, I guess, such a small footprint. That was really wonderful. And we're hoping that this series will inspire other institutions to also adopt geothermal. But we do understand that a lot of institutions see making the change from gas to a more sustainable energy source as financially not feasible, and you've spoken to some of those challenges. What advice would you give to those who are thinking about both short-term and long-term financial benefits and restraints to this change?
Sure. Geothermal system will pay for itself. I will just say that. I mean, it's kind of all based on a lot of factors, and we run an energy model for the building. So we look at how the envelope performs, and then how much energy it takes to operate the systems against a conventional system and a geothermal system. That's usually one of the things when you get a client that's on the fence about going conventional versus geothermal. Almost always the geothermal system operates with less energy. We just say it that way. But the cost of energy is different depending on its gas or electric. And so sometimes, just because of the nature of the utility rates, it might be a 15 or 20 year payback, efficiency, less operating costs, but to cover the differential in cost between the conventional and geothermal system, it might take 15 or 20 years, or sometimes longer, to pay it back. And usually if you're doing more than 10 years, people get nervous, because the equipment life is about 20 years. And so, it's hard to pull the trigger when you're gonna, about the time you need to replace the equipment, you're finally paying back. But most equipment lasts for 20 years. So your conventional system is probably being replaced at about that same time cycle, maybe less, because in the case of Geo, all my equipment's indoors, where there's air conditioning. The systems are sitting with equipment outside, and gas-fired equipment has heat exchangers in it, that sometimes will burn up the heat exchanger and have to be replaced sooner. So my general comment is, if you can afford the long horizon of payback, and sometimes it's less than 10 years, just depending on the area of the country and the type of systems you're comparing against. But if you can afford the horizon and you can come up with the additional capital cost up front, which there are grants to help with often, and state rebates or utility rebates and things like that, you can usually get better control with less operating costs and long-term savings if you go with the geothermal. It's easier to configure a geothermal system to provide that simultaneous temperature humidity control, for instance. Much harder to do with a conventional system, because I don't, in one case I have a box that's designed to do both, and so I can move things around to make that work. If I want to do it in a conventional system, I'm kind of often forced into the chill water, hot water model, which costs more to install. In some cases, geothermal is actually less costly than the alternative system that will give you the same performance. And so if that's the case, then it's a 0-year payback, and I don't usually have trouble selling that project. But there are ways to do it, and the challenges with historic properties is they usually struggle. They can often get the money to do the project through grants, and people who are really interested in sustainable practices will fund a project like that. But there's maintenance involved and maintainability, and it's usually a little more complex control-wise than a conventional system, or can be. And so you have to be prepared for the ongoing cost of operation, in addition to, now, I will say that, again, geothermal should be less expensive to maintain because it actually has fewer components and doesn't have that outside piece and stuff like that. And the geothermal loop itself is kind of a forever piece of equipment. So once you've installed it, you don't have to replace it. When the equipment fails, you just replace the equipment. And so once the geothermal, the piping has a 50+ year warranty. Of course, doesn't help you when it's 500 foot in the ground. They'll give you the piping. That's not the expensive part. But we don't see a lot of system failures, loop failures. There's a backhoe tears up a loop, but really not much else during normal operation causes the loop to fail. The trickiest part of a project is getting it inserted into the building. And again, I have to do that with any system I'm going to put in. So if I'm going to put a conventional system in with ductwork, I still have to insert it into the building and do it in a way and that almost always costs more than just somebody's house where we're installing a system. So what they have to look at is what is the best, what are they ultimately looking for as far as climate control, and then they should do a study. We always recommend a front-end study, assess the systems that are in place, assess the feasibility of putting in a geothermal system. Do they have the land available to put the loop field in? Do they have the places to hide the equipment? And that's, again, we usually look at geothermal and a couple of different iterations of conventional systems, and then try to come up with recommendation on efficiency and long-term operating costs. We look at a 20-year life cycle. So we try to bring all the costs in there and then decide what the payback is. So, but ultimately it's what are the goals of the institution or the organization or the people running the building. Again, if temperature and humidity control is involved, your system's going to get more complicated. The least complicated system to do that is a geothermal heat pump with a forced air system with a standard heat pump installed in a geothermal heat pump. As soon as I introduce chill hot water as a source, which works good, and it works in either conventional or geo, that solution is going to be more complex. Controls are going to be harder. So the controls are always a tricky part. We did I'm blanking here. We put in a geothermal system at Unity Temple, as I mentioned earlier, and that system it was very costly to maintain. And the reason it was costly to maintain is I had 20 air handling units in the building. I have 8 fan coil units, I'm sorry, almost 20. I have 10 air handling units, and I have 8 fan coil units, and each of those has to be controlled and all that stuff. And I was questioned about it by the organization that funded the project or helped us fund the project, and they were questioning, why is your geothermal system so expensive to maintain? I said, it's not. The parts of the system that are hard to maintain or expensive to maintain would be there in a conventional system or a geothermal system. It's not. It's the only thing that makes that a geothermal system is a loop field instead of a cooling tower. And that cooling tower would be more to maintain, more expensive to maintain than the loop, which has no maintenance required. So you just have to look at it holistically. And sometimes it's hard to convince people. Another problem is that a lot of these old buildings aren't air conditioned. And so when I have to speculate, I have to design in my head, I have to design a conventional system that would do it, and a geothermal system would do it when I'm doing this modeling, this energy modeling. And when they see the cost of operating, the utility costs, they go, well, that's not right. It didn't cost us anywhere near to operate a building like that. Well, you're only heating the building. And I'm going to air condition the building. And if you do it conventionally, it's going to cost you more to operate than it does to geo. And that's the point of the survey or the study is to prove that. So it's, but you have to look holistically at it. You have to look, and don't be scared off of the pricing. I mean, it certainly is going to be more cost to install a geothermal system, but you will recover it. If you're a long-term ownership of the building, even better. The hardest sells I have on geothermal systems are developers, because they want to turn around their money in a hurry. So, and they want to get whatever they spent on it onto the other side. And so it's very, very hard. Even with very quick paybacks, they're not interested usually. But, historic building owners, governmental agencies, churches, people are going to own their property for a long, long time. Homeowners, those are absolutely perfect candidates for geothermal, because it will pay itself back, and it stabilizes out that utility cost across the year.
That's really good to know. Actually, I think that's a really important thing for cultural institutions to keep in mind. One thing that you mentioned that I would love to just get a little bit more clarity on, I guess, or just expand on a little bit. Something that we conservators, as I've mentioned, love to talk about is temperature and humidity controls. And as folks who are concerned about sustainability in this realm, one of the things that we've really pushed for is for a model of seasonal drift, where we've, as a profession, have studied how these fluctuations impact objects, and found that over time, a slow drift is definitely, preferable to a sharp
Right.
up and down. So I'm curious. Obviously, geothermal is much more energy efficient and much better for the world. But is there a sense that you can keep a tighter control? Is that what you're suggesting, or is that not necessarily the case?
Well, it's not necessarily. You can get very tight control. You can get just as tight a control with a conventional system than you can with a geothermal system. It's usually easier to do with some geothermal systems because, again, that self-contained unit, which has got the compressor and the fan and just blowing cold air or hot air, can be configured so that it's more or less automated. You have a thermostat on the wall that has a relative humidity sensor in it, and it's as simple a system as you can get, and it almost always operates better than most. And I can get pretty decent relative humidity control. Again, it's that idea that not overcooling the space while I'm trying to bring humidity down. That's the trick. And in order to do that, if it's a conventional system without that feature, without either the coil placement, chilled coil first, hot coil second, when the temperature satisfies, the system shuts down. So it's just harder to do. And again, I can do a chill hot water system with Geo, and I can do just a forced air system with self-contained equipment with Geo. And the comparison to that it compares with residential type systems in the sense of usually it's a gas-fired furnace and then a cooling coil. And because of that configuration, I don't get that reheat function on the other side of the cooling coil. Cooling coil sits downstream of the heat of the gas heat exchanger. So I can't pre-cool the air and then warm it back up with the gas-fired heat exchanger. That doesn't work. So then I have to introduce another piece, either a hot water coil or electric coil, which costs a lot to operate. I have to introduce that piece downstream of the cooling coil. So it's just a little trickier. You can do it. Sometimes what we'll do is we'll We were working on some 1840s Latter-day Saints houses restoration in Nauvoo, Illinois. And we did geothermal, but we had no place to put ductwork. And so we had to use what's called a variable refrigerant flow system, which is a fancy box. It's a box in the basement, and then refrigerant line sets run up to units that are mounted in the attic. So I only had to find room for that refrigerant line set. But I can't get any reheat control on those. So I have to introduce reheat on the other side. And it's a smaller system, and humidification is trickier because it's usually a small ducted system. And so it just gets harder. It's certainly doable. To really get really good control of that seasonal drift, then you really need a building automation system where I can put in different thresholds for, because what happens is, I'm sure you know, is that we'll have a lower humidity in the wintertime inside the space, because we can only achieve so much before the building starts to basically say, I'm done. We get condensation on the windows. If you're getting condensation on the windows, you like to get condensation inside the walls. And so you have to be really careful with that. So there's usually a maximum humidity that's outside the range, and a historic building is often outside the range of what you'd like to see. But it's better than it would be if you didn't do anything. And then on the other side, it's pretty easy to get the humidity out again with the system concept. But a building automation system can do a little bit better job of adjusting that set point to what's reasonable at the various times of the year, whether it's winter, spring, summer, fall. But the simple thermostat does a pretty good job on the self-contained heat pump. And again, we're trying to shave the peaks off, the high. I can get rock solid temperature control, at least at the thermostat location. So if I got a simple system and it's one box and one geo heat pump or furnace, air conditioning, I can wherever that thermostat's at, it's going to be within a half a degree of set point almost all the time. Rarely is it going to be outside that range. The relative humidity is extraordinarily challenging because it's influenced by outside. It's influenced dramatically by how much infiltration I have into the building. So an outside air, it comes in, and so one of the things we recommend is, usually on historic properties, we usually recommend a data temperature humidity campaign be introduced before you make an intervention, and then keep it going, and then continue to monitor. And then after you've made your intervention, it gives you the ability to tweak your set points and things like that to try, and gives you the documentation you might need to prove that you've improved the situation. And when we do that, we still see, because it's still driven very much by outside conditions. So the better I can do about infiltration control, air infiltration control, and if I can avoid having to bring in outside air into the system, then the better control I get ultimately. But it's interesting. I did a study, a long-term 2-year study, another NEH grant at Napier Settlement in Naperville here in the Chicago area. And it's a cluster of historic buildings that have been brought to this estate site. So the original building is this beautiful brick mansion. And then they have all these things you typically find in a village, that have generally been existing buildings have been brought there, sometimes replicas. But so you got the lawyer's office is this wood frame house that you stand inside and you can literally see to the outside through the clapboard siding. It's that bad. And then we have a masonry house that's 2 stories, and it's pretty well put together, but they're both about the same age. So we did blower door tests on those. So we try to figure out how much infiltration we get. And the brick house did pretty good, almost to modern standards, acceptable, which is not uncommon because the only place it's going to leak out is around the windows and doors. And that frame house had about 4 or 5 times the recommended level of infiltration. And then we had two modern buildings in their campus that were designed to house artifacts. But the systems were never really designed to house artifacts. And so the worst system we had in the entire complex was the warehouse designed for artifacts. The best system we had in the summer was the house that had so much infiltration, because the system was constantly on. And so it was constantly removing humidity. And so I was flatlined on humidity. It had better performance, less time out of range than any other building on the campus. In the wintertime, of course, it was just the opposite. It was as dry as it could be because I had all that air. So the recommendation was take it offline in the wintertime, let the temperature drop to 40 degrees and do, a humidistatic control, which you let the temperature drop and the relative humidity comes up. It comes within range and you just take it offline as far as tours go. So, so we were able to do minimal recommendation that required minimal intervention to the building and still get decent control when they needed it. So it's that approach of sometimes every building's unique and different, but you really have to look at it and you have to study it, to spend time at the building, and you have to, data is a powerful thing. So before and after. So.
Awesome. Well, I love to end on a sort of energizing inspiration note. I know you're more of a engineer type, but I'm curious if you have any thoughts on just how, how the preservation and cultural institutions can lead in sustainability. Is there sort of an area where you can really, innovate? And
I think as an example to the general population, because let's face it, the majority of housing stock or building stock in the country is old, and it's maybe not 120 years old or 100 years old. Maybe it's only 50 or 60 years old, but usually it's still built not well as far as insulation and current sustainability practices. So as an example to a community, it can be very beneficial to show them how you can integrate modern systems into historic buildings without destroying the integrity of the building. And it can be done in a way that's not offensive. It can be done in a way that's maybe even aesthetically pleasing if you do it right. Maybe very little aesthetic impact. You can improve, a lot of these sites are gorgeous, in the summertime, people like to wander around the gardens that are there. And then I got a big condensing unit sitting there making this horrible noise. And so you can get rid of all that as an example. People can enjoy their outdoor spaces that still have conditioned indoor spaces. And that's true whether you have your deck or your patio out there, or whether you're a cultural institution where people are enjoying the grounds. I think primarily because also you're serving a public and you have an educational component to most of these historic properties. And so again, as an example you can be an example to the community of a way to be sustainable even in an old building and take the steps. And the best projects, I think, are the ones that integrate that component, because it's not just putting in the system, it's putting the system correctly. Because if you do it wrong, you can do more harm than you do good. So it's really important to do it correctly. So you can be cultural institutions or historic properties can be a real community asset in demonstrating and educating the general population on what you can and can't do. And
well, that's super inspiring to me. I know.
Yeah, if they can do it on their budgets and be good stewards of their buildings and sustainable practices, that's the best example you could hope for.
Oh my gosh. Well, on that note, I feel my heart is warmed.
Good.
I so appreciate you taking the time to speak with us. This is absolutely mind-blowing. I have to process and probably rewatch this just to
well, and if you got
sure I taught everything.
Yeah, sure. If you got follow-up questions, please don't hesitate to reach out.
Amazing. Well, yes.
It's important to me to help inform and educate because there's way more buildings than I could ever possibly work on out there, and helping prevent mistakes being made, because you just got to find the right people to do it. And there's people like that in most communities. Maybe not as many engineers, but a lot of these contractors really know their stuff. Mm-hmm. And so, although historic buildings tend to be special, so you're trying to make sure you do it right.
Well, we thank you very much for your commitment to this work, because it's really great to have people like you as a resource. So thanks again for speaking with us, and I'm sure I'll let you know when this is up and everything. And,
okay, great.
Yeah.